Greetings to all. Today, myself, Bhavyan Sharma. I'm here to present on the topic Fermat's and Euler's theorem. So first of all, by the definition of Fermat's little theorem, what does it means? So it basically means that if P is a prime number and A is a positive integer that is not divisible by P, then A to the power P minus 1 is congruent to 1 mod P. So what do we mean by that? Is that P and A are relatively prime to each other and P is a prime number, then A to the power P minus 1 is congruent to 1 mod P. Now, to understand it further, we take an example. So the example is, does Fermat's theorem hold true for P equal to 5 and A equal to 2? So first things first, is P a prime number? Yes, 5 is a prime number. Is A a positive integer? Yes, A is a positive integer because A is equal to 2. Now, does P divides 2? No, 2 doesn't divide P. So we satisfy all the three conditions and hence it should satisfy Fermat's theorem. Let's do it. So given P equal to 5 and A equal to 2, A to the power P minus 1 is congruent to 1 mod P by the definition of Fermat's theorem. So 2 to the power 5 minus 1 gives us 2 to the power 4, and modulating it with 5, that is 16 mod 5 would give us 1. So we hence prove that Fermat's theorem holds true for P equal to 5 and A equal to 2. Let's take another example here. So we have P equal to 13 and A equal to 11. P is a prime number and A is a positive integer, and P doesn't divide A. So all the three conditions are satisfied here also. Hence, it should satisfy Fermat's theorem. Now, further solving it, 11 to the power P minus 1 is 11 to the power 12 mod 13. Now, there are many ways in which 11 to the power 12 could be calculated and then modulus by 13 can be taken. One of the methods being 11 is falling short of 13 by 2. So we take minus 2 to the power 12. Now in this case, 12 can be written as 4 into 3. Minus 2 to the power 4 is nothing but 16. 16 when modulus by 13 gives us 3. So we have taken here 3 to the power 3, which is nothing but 27. And modulus of 13 with 27 gives us 1. Hence, we have proved that Fermat's little theorem is also satisfying here. Once again, 11 to the power 12 is congruent to 1 mod 13. This is by definition. And now we have to prove it. 11 is falling short by 13 by 2. So we take minus 2 to the power 12. Then minus 2 to the power 12 can be written as minus 2 to the power 4 into 3. 2 to the power 4 is nothing but 16. When modulated by 13 gives us 3 to the power 3, which is nothing but 27, and 27 modulus 13 is 1. Now the last example for Fermat's little theorem, and we have to prove that for P equal to 6 and A equal to 2, Fermat's theorem is not applicable. P equal to 6 is not a prime number. Hence, our first condition is invalid, is false. Second is A is positive integer. Yes, A is a positive integer. So second condition is fulfilled. Third condition is A is not divisible by P, which is also true because 2 is smaller than P and hence not divisible by P. But because of the first condition being invalid, hence it would not follow Fermat's theorem. Let's prove it. 2 to the power 6 minus 1 is nothing but 2 to the power 5, which is equivalent to 32. Now 32 modulus 6 or P gives us 2 and not 1. Hence Fermat's little theorem has been violated. So P equal to 6 and A equal to 2 doesn't follow Fermat's little theorem. Now moving on to the Euler theorem. Actually, Fermat's theorem is a specific case of Euler's theorem. In broad terms, Euler's theorem has a bigger applications than Fermat's theorem. To understand it further, let's understand what does Euler's theorem tells us. So, Euler, by the definition of Euler theorem, for every positive integer a and n, which are said to be relatively prime, in Fermat's theorem, the condition was that n should be prime and a shouldn't be divisible by n. And here the condition is that a and n both should be positive numbers and relatively prime. What do we mean by relatively prime? The meaning of relatively prime is that the GCD of a and n should be nothing but 1. GCD is greatest common divisor. Then a to the power phi n, the phi is a constant, and we would understand how to calculate phi n is congruent to 1 mod n. Now let's understand it with an example. So the example is prove Euler theorem hold true for a equal to 3 and n equal to 10. So the three conditions are a should be positive number, yes, a is a positive number, n should be positive number, yes, n is a positive number, and the third condition is they should be relatively prime. GCD of 3 is nothing but 1 when taken with 10. So both of them are relatively prime with each other. Let's understand. So putting the values in the formula, we get 3, 5, 10 is congruent to 1 mod 10. Now, how do we calculate phi 10 or phi of something? So phi of something is calculated by taking the prime numbers, like phi 10 can be written as 2 into 5. These are the prime numbers in which 10 can be broken. Now, what we do is, what is the formula is, we take p minus 1, that is the first prime number, into q minus 1. So p here is 2. 2 minus 1 is nothing but 1. And q minus 1 is 5 minus 1, which is nothing but 4. So here we're getting a value of 4. Now solving it, 3 to the power 4 is 81. 9 into 9, 81. Modulus of 81 by 10 gives us 1. So this the condition is satisfied. Hence, Euler's theorem holds true for a equal to 3 and n equal to 10. Let's take the second example for a equal to 2 and n equal to 10. So, are they relatively prime with each other? No, because 10 has a GCD of 2 and a does also have a GCD of 2. Hence, this shouldn't be following Euler's theorem. Now, let's understand it. A phi n, that is 2 phi 10, is congruent to 1 mod 10. Phi 10 is equal to 4. This is the value that we calculated here, that is 4. So we are taking it here. So 2 to the power 4 is nothing but 16. 16 modulus 10 gives us 6, which is not equal to 1, and hence the Euler's theorem doesn't satisfy. The final example that we take is a equal to 10 and n equal to 11. So does they satisfy Euler's theorem? Let's find out. So we put here 10 phi 11 is equal to 1 mod 11. Now calculating it, what we get is, how can you write 11? How can you write 11? 11 is itself a prime number, correct? So 11 can be written as p minus 1. P minus 1 is nothing but 11 minus 1. 11 minus 1 is nothing but 10. So we are getting answer as 10. So 5, 11 is 10, 10 to the power 10. Since it is it would require a calculator for you to calculate, you can find a shortcut to calculate 10 to the power 10 when you have to take modulus by 11. How can you do this is, it's falling short by 11 by how much? By 1. So you write it minus 1 to the power 10. Now since 10 is an even power, which means that minus 1 is multiplied by even times, which brings us that minus 1 minus multiplied even times is positive. So we would get here positive 1. Now positive 1 modulus 11 is nothing but 1. Hence it is solving, it is following the Euler's theorem. Now let's come up to the applications of Euler and Fermat's theorem. So Euler's theorem is being used in RSA crypto system, which is widely used in internet communications. In this crypto system, Euler's theorem is used with n being a product of two large prime numbers, and the security of the system is based on the difficulty of factoring such an integer. So RSA crypto system is using Euler's theorem to compute the factors of two large prime numbers. And Fermat's theorem, since I told you that Fermat's system is a specific case of Euler's theorem, so basically it's a subset of Euler, and it's being used in the validating and testing of primary and public key in cryptography. So these are the application of these two theorems. I hope that you got the gist and understood the algorithm, understood the theorems well. So this is from my side. Thank you.